All right. So what was the homework assignment? Which functions for linked list? Oh, display the list in some sort of reasonable way. Okay, okay. Don't I already have some stuff written? I'll do it one of these other ones. Well, I thought it'd be in the link list. Okay, so here is, now is this, do I have this saved under my projects? Am I logged in as a different person here? This all popped up, but under my projects. Yeah, it's like I can't get to that directly. Oh, well, whatever. Okay, so right now I have a display. When I go to run this, it shows nothing, right? Before it showed empty list if I didn't put anything in there. So I think if I comment these dudes out here, what is this? Do I not get the? Now do I have a project? Save. Linked list homework. So if I comment these guys out here, I'll get the empty list. So there's my empty list. But as soon as I put at least one thing in there, nothing displays. Because I'm not getting into the else of my display function. So if it's null, print out the empty list. Otherwise, there must be stuff in it, right? There's stuff in it. I want to go ahead and traverse the list. So else, I want to traverse the list and ask each node to display itself. So under node HPP, notice here I've written a function called display. So with node CPP, the display function prints out this node's payload and then kicks it down a line. So one thing I can do here, so I'm going to write this a couple of different ways. I'm going to let the top level linked list go through and display, ask each node in the list to display themselves. So I'll do something like node pointer cur node is equal to the head of the list. So start at the beginning of the list. So I'll say while cur node is not equal to null, as long as it's a real thing, what am I going to do? I'm going to tell cur node to display itself. And then I'll set cur node equal to get next node, right? Get next node. So I'll tell the current node to display itself, and then I'll set current node equal to its own next node. So current node will just hop down the list, one node at a time, telling each node to display itself. So I'll go ahead and undo these guys. So I should get 4, 3, 2, 1 as the contents of my list. There's my 4, 3, 2, 1. All right, so that's one possible solution, but I'm going to say that wasn't the cool kid solution. That was the easy solution. The other one's relatively easy too, but the other one gets you starting to think recursively. Okay, so what I'm going to do here is if I'm not in the empty list, I'm going to ask a node to display itself. Now that node knows about the next dude, right? He knows who comes next in the list. So can't he then ask the guy next door to display himself? Who then can then ask whoever his neighbor is to display himself? Who can then ask whoever his neighbor is to display himself? And finally, when we get to a node that doesn't have a neighbor, he can say, this is the end of the road. I'm done. And that'll allow us to get some like kind of some arrows out there for like a visual linked output. All right, so rather than this syntax, I'm just going to say this head display. I'll ask the head of the list to display itself. Now I need to go into my node and update what does it need for a node to display itself. Well, right now a node is going to print out its payload. Now I'll go ahead and put a little space there at the end. But now I'm going to ask a question. If this node's next node is not equal to null. So if I'm the node and I just displayed my payload, and then I ask the question, do I have a neighbor? If I do, what am I going to do? I'm going to say cout, and I'll draw a little arrow in here like that, just to kind of give us a visual of links. All right. And I'm going to ask my next node, actually, I won't write it like this. To display himself. So if I have a neighbor, draw an arrow and then ask my neighbor to display himself. Now, I could do something like this if I prefer. I can draw the little arrow here regardless. And then say, if I have a next node, tell him to display himself. Else, we can just do something like a cout null. And this will be like the end of our fake C recursive calls. It's not technically a recursive call because I'm not calling my own display method. I'm calling the next node's display method. So it's kind of a recursive looking call here, where I call the next node's display method from within my display method. But when I finally run out of neighbors, I'll just print out that I finally point to nothing. The end of my list points out to oblivion, and then kick it down the line. All right, so then back here in main, I'm sorry, back here in our linked list, to print out my whole list, all I do is tell the head to display itself. Go ahead. Head doesn't have a who? Sure it does. What's head? Head is a well, head's a node. It's not the payload that has a display method. It's a node that has a display method. So head is a node. So if I'm in this function here, head is equal to something other than null if I'm in this else, right? So what am I going to do? I'm going to tell head, which is a node pointer, to call his display method. And head does have a payload, because when we first added something to the list, what did we do? We made head point to the same place that temp pointed to. So head only holds a memory address that points to an actual node, and nodes have payloads. Does that make some sense? So during this exact little moment of time right there, temp and head both point to the same place in memory. We have two different ways of getting to that dude in memory. As soon as this addFront function died, temp disappeared. He was reclaimed by memory, but head persisted because it was a variable established at the class level. He's a more global variable. He didn't live and die with my addFront method. Yeah, so the important concept here is that head does not hold a payload. Head holds a pointer to a node which has a payload. Make sense? This is just more pointer stuff. So what I'm saying down here in display is I'm saying this dot head is a node. Tell that node to display himself. And maybe to drive the point home with the arrow, if I said that, this dot head like that, now we'd have trouble, because now I'm trying to treat the variable head as if it's a node, as opposed to as if it's a pointer that points to a node. So by saying, in order to do that, I would have to say star this dot head. Sorry. This guy. That's always going to be like that. Star this dot head. This says resolve. No, I had this right. That guy. If I wanted it to work this way, I would have to resolve it using that syntax. Instead, I wrote it with my arrow syntactic sugar and said, take the variable this, resolve it to the head value, resolve that to the node that has a display function. So there's my nodes telling each other to print themselves. So this was head, me originally asking head to display itself. It displayed a 4 followed by an arrow. If I go into node here, it displayed a 4 followed by an arrow. And then I asked the question, does 4 have a next node? Is his next node not equal to null? It's not equal to null. So what do? I ask his next node to display himself. And his next node is this guy 3. So that comes and calls 3's version of display, which prints out the payload followed by an arrow. This right here. Then I ask the question, does he have a neighbor? If so, tell his neighbor to display himself. So his neighbor, which is the 2, displays himself. Then we ask, does he have a neighbor? If yes, then we go and say, have his neighbor display himself. So that's the 1 followed by this. Then we say, does he have a neighbor? No. So that's where we get into this else. We output the null and finally kick it down a line. We stop calling those extra functions. So 4 calls his neighbor, 3 calls his neighbor, 2 calls his neighbor, 1 has no neighbor. So finally hits this code right here to end. And we get maybe a little bit prettier looking linked list looking thing. You could have pulled that off the other way too. But we're effectively handing off the buck. We're saying, hey, you want to display the list? No problem. What does linked list know about? Linked list knows about the front of the list. That dude knows who's next to him. Who knows who's next to him? Who knows who's next to him? So on and so forth. It's the nature of a linked list. All right, makes some sense? All right, so a couple different ways to solve the homework assignment. Just getting practice with pointers there. I probably like that way a little bit better. It's good practice to start thinking, you know, as third semester programming students start thinking recursively a little bit. Even though, like I said, recursion is technically when a function calls itself from within itself, where in this case, it's a node calling another node's same method. So it's not quite himself, it's halvesy recursion. All right. Well, let's go back to our linked list here and say, okay, well, what should come next? Well, we have the ability to add something to the front. What if we want to remove something from the front? Maybe we can go ahead and we can say, let's have it return the payload. If I'm going to remove something from the front, maybe I want it to go ahead and give the value that it just removed in case you want to use it. Seems reasonable enough. All right, remember, we are writing this data structure, so we kind of get to decide how we want it to look. We're holding on to our linked list here. We take something off the front of it. We might want that value. So we'll go ahead and spit out that value. So it's got to return an int because we have a linked list of integers. And we'll call this guy removeFront. He doesn't require any parameters. We'll go ahead and implement this inside of here. Oops, sorry. There we go. All right, so we'll just work with our visual right here. If I say remove front on that list, and then I tell the list to display itself, I should have a 3, 2, 1 null left over after I've removed the element from our list. So how do I actually go about removing something? What does it mean to remove an element from a list? What are we accomplishing when we remove an element from a list? In order for the new list to be just this guy here, what must be true about head at the end of remove front? Head must point where? If what I have highlighted here is my new list, where is head pointing to in this list right here? Pointing to the 3. So that means if head started off pointing to this 4 before I removed it, when all is said and done, I needed to point to this 3. Okay, so we need to make sure that we keep track of where it's old to where the new front is going to be, disconnect the old front, keep track of the value we're going to return, and make sure everything's updated before we finally return. So I'm going to go ahead and store in an int. Now we can do a bunch of error checking here and say, well, is there a front? So maybe we say, you know, if this head, well, maybe we ask if it's equal to null. That means it's the empty list. And at that point in time, maybe we say cout can't remove front from an empty list. You know, some kind of error message, something like that. Just do a little error checking. All right, so we're still alive there. I can go ahead and just do a return if I wanted to. I don't have to, but because it'll just die naturally here too. All right, if I'm in this else, that means I actually had a list that actually had a front that I actually need to return. So I'm going to preserve the value that we're going to be returning. So int val to return, and this is going to be the heads payload. Get the value that the node that head points to currently holds. That's what this dude will be right here. Make sense? Now, I'm going to go ahead and give myself a node pointer called temp. One mindset we should have when we're working with memory is that we should clean up memory. There is the reality is in modern computing, there's a lot of things that might get done for us. And if we're working with a certain platform all the time, maybe we could say it's okay to let it go ahead and do certain things that we know it will do for us. But generally speaking, especially now as we're just getting used to working with pointers, we want to make sure that we always clean up our own messes. Okay, so what that means is, I go back to my slides here. If I am removing this guy from my list, not only do I need him, I'm just going to kind of do this. Not only do I want head to now point to the next guy, but I want this guy to disconnect himself. No longer is he a player in the list. That makes sense? But if we draw our pictures here, we have to think about the order of operation. What if I set head equal to head's next node? What did I just lose track of? Do I have any way of getting to this guy anymore? In this picture, no, I've lost access to him. He still points to this dude, but through my variable head, I have no way of reclaiming this guy. I can't get back to him. I can't tell him to disconnect his arrow because I have no way of I don't have a pointer to him. Does that make sense? So we need to be careful. That's where the pictures come in. So I can't just do that. I can't say head, point to the next guy, and then go back and fix this guy up. That's not going to work. Well, I said my ultimate goal is to make this guy point to null. So I can go in and say, oh, well, head point there. Well, now I want head to point to this guy's next node. Uh-oh. I lost track of the next node. So now I have, by giving myself access to this, I can no longer get back to here because I've lost the pointer to it. So what that means is I'm going to have to give myself another pointer to temporarily hold the current head. So maybe I call this guy temp. And I make temp point at the same thing head points to. Then I can update head to point to head's own next node. Then I can update temp to set his next node to null. Does that make sense? I had to make sure I held on to all the kite strings. Okay? Can't let go of that kite. Go and do something here, then expect to ever get that one again. It's floating off. Make sense? All right, that's where drawing pictures is going to be pretty important for you for a while now. And as these lists get more and more complex, it's going to be important for anybody. When we start adding and removing in the middle of our linked list, it's going to be even more important. But even when we're solving the relatively easy problem of adding and removing from the front, we still have this mini example of, hey, Don't let go of a kite string before you've grabbed onto it with a, tied it to a fence or something, so you can, get to it again. All right, so go back to my code. So I'm going to give myself my temp node. I'm going to make this guy point to the same thing the head currently points to. All right, so that ninja move right there. What's flashing back here? Let that cook in the background, I guess. I thought that maybe was the cause. We'll just keep going. All right, so the ninja move I just did there is this first part right here. I created a second pointer called temp and made him point to the same place that head points to. Okay. Temp equals the value stored in head, which is the memory address. So now both temp and head both hold the memory address. Specifically, it's the same memory address, and those addresses point to the same node. Then I can go ahead and I can say, head is equal to head get next node. I can update the value head, which is a pointer that knows how to hold the memory address of a node, to be the address of the current node that head points to's next node. That's this ninja move. Head is equal to his own next node. Make sense? All right. Finally, we can now say temp set next node to null. So we'll say temp set your next node to nothing. All right, that makes some sense. Now, we'll roll with this for a second. We'll go ahead and return the val to return, which should be the number we just removed. And we'll come into main here. So we just displayed the entire list. So now we'll go ahead and do a cout of LL remove front. And we'll tell the list to display itself again. Oh, I need to. Give myself access to see out here. Do I need to just not return a value? Probably. All right. So there's my original list, 4321. Here's evidence of me outputting the result of calling removeFront, which return that int, right, that I removed. So there's the 4, that's the dude I removed. And then proving that we're left with a functional list. I went ahead and told the list to display himself again, and we see we have the list 321. All right, but now technically, what we have right now is a situation where when that function ended, when removeFront ended, this variable temp disappeared. All right, so now we have something in our operating systems called a pointer counter. When temp and head both pointed at this memory address, the pointer counter for this guy was 2. 2 separate pointers pointed at this memory address. Once we made head point here, his pointer count decremented to 1. When the function ended, his pointer counter, so this variable temp, disappeared. Why? Because that variable was born inside of removeFront right here. He was defined here, so he ended. He was deleted, or he was automatically deleted at the end of that function call. Make sense? So that means that when this guy disappeared, this place in memory now has a pointer count of 0. Now, this place in memory still exists. If you are the operating system, what do you do with a bucket of memory that has a pointer count of 0? What does a pointer count of 0 really mean? If nothing is pointing at a place in memory, what does that mean about that place in memory? Does anybody have access to it? Nobody can get to it, right? So even though we see that this bucket of memory, remember memory works like a big long street. So you have a big collection of memory addresses. So even if memory address 17 has a house built on it, if nothing currently points at that house, if nobody knows how to get there, that house is now memory that's being filled with something. It's holding a value, but nobody has access to that value. So would it be fair to say that if there's a house built on the street that nobody currently has access to, that we would be free to go ahead and knock down that house and give that land to somebody else who might need it? Nobody else can use it right now. Sure, there's already a house there, and maybe we're not just going to waste our time demolishing a house that nobody needs that space right now. But for the moment, we can at least mark that space as being available land, right? So the operating system can go and sweep through memory. Maybe they have a Java uses something called an automatic garbage collector. So it's a computer program that sits there and looks through memory and identifies buckets of memory that nothing currently points at. So with C and C++, in this case, C++, more modern runtimes for C++ would do something like that. They would go through here. Well, really, it's the operating system. It would go through here and it would say, I've noticed a chunk of memory. There seems to be a value there. Its pointer count is 0. Nothing points to it. I'm going to go ahead and check with the memory manager of the operating system and say, hey, did you have this memory address 100? Did you have that marked as currently being used? The operating system is going to go and look it up. And then maybe in this case, they say, yeah, we did. Somebody else is already using that. But then we say, you know what? We just checked. Nobody has access to it anymore. So they've skipped town, but they've left their mess behind. So the operating system can go and clean up the mess then. Either delete the value living there, but at the very least, mark in the operating system as that plot of land, memory address 100, as being available to hand out to somebody else. Then potentially they could, destroy the value that's already there and reinitialize it to a null value or something like that if they wanted to. I would be an advocate of this. We just abandoned this memory. But right before we abandoned it, it might be nice for us to notify the operating system to save it some time later on that, hey, in a second, when this function ends, nobody's going to point to this dude. Go ahead and delete this place in memory. Give it back to the operating system manually so that you don't have to rely on the operating system's extra horsepower to go and find it later on. So as of right now, the way we have this code written, this guy right here, at the end of this function, when temp goes away, we technically have something called a memory leak. We've left memory out there that has something in it that nothing can get to. All right, so we have a value that lives out there. Now, in this case, it's a little linked list node or something like that that we can say might be relatively unimportant. But what if it's something that holds like a password or a credit card, a piece of credit card information? Technically, that still lives in memory. So if you wrote a program that started walking memory, looking at each bucket, you could stumble across somebody's credit card number or password or something like that. Okay, the attacks for that is something called the buffer overrun. Okay, or buffer overflow, where you get access to memory that you legitimately have access to, then you run off the end of it. And we saw that in class a couple times ago, where you can just run off the end of it and you can start accessing things that you were never handed, but still technically exist. Good programming practice might say, look, if you're done with using memory, go ahead and delete it. So before we're done here, we'll go ahead and tell the operating system to delete temp. And hopefully this online GDB supports delete. Yeah. So in that particular case, so all I did here is I knew temp was about to die off. So I went ahead and said, you can go ahead and give back this memory and wipe it clean. So somebody else can use it because I'm done with it. So in that example, this guy disappeared. We secured our data, if you will. That would be good programming practice. And we would have said historically that would have been necessary programming practice. Today, there's probably a subsystem in modern operating systems that goes through and manages your memory and tries to say, hey, here's 11 pointers that were abandoned. Here's 11 memory leaks that I found. I need to go ahead and clean those up because nobody else is going to do it. That makes some sense? So this falls into that category of something that we aren't used to doing when you learn a newer language first. When you learn something like Java, which doesn't even have a syntax for deleting memory. Java just relies on automatic garbage collection. So as programmers, we don't necessarily get into the practice of cleaning up our messes. So that, like right now, we might say, oh, we're going to get into the practice of cleaning up our messes. And then once we get to a language like Java, where it's doing it for us, we really appreciate, it's kind of like having a maid, right? They clean up your messes at your house, things like that. So then you start getting into, you get lazy and you make messes, don't even think about cleaning them up, which maybe isn't great either. My wife's not a fan. But the point is that at least we can appreciate the work that's being done by the automatic garbage collector. All right, so questions about removeFront. All right, so next thing we might do is we might write what? addEnd. Let's add something to the end of our list. Void addEnd. This guy will take in a payload. All right. So if I'm looking at my linked list here, I'll just reconnect everything up so I never know when I need those things again. All right. I'm looking at my linked list here. I ultimately want to add something new to my list way over here. So let's say I want to, the payload that was passed in was a 14. So we're going to go ahead, we're going to create a brand new spot in memory. For this. So I'm going to go ahead and create my node that's going to hold this. So I'm going to say node pointer n is equal to new node built with that payload. So I'm adding it to the end. First thing I need to do is I need to go ahead and generate a brand new node object and endpoints to it. Right, so that's what I got right there. This is n right now. That's n. Okay. Ultimately, what I want to have happen is I want this guy to point here. That means I've added it to the end, right? So then my question is, how do I get to this guy in order to tell him to point at the same thing n points to? Who knows about this guy? Just look into this picture. Who knows about that guy right now? Guy before him. Okay, who knows about that guy? Guy before him. Who knows about that guy? Guy before him. Who knows about that guy? Guy before him. Who knows about that guy? Head. So we're going to have to traverse our list, run from the beginning of our list from head all the way to the end of our list until we finally get to a node. How do we know we're at the end of the list? What are the characteristics of this dude that tells us he's at the end of the list? Points to null. All right, so I need to zip down my list until I get to a dude that points to nothing. All right. Now, I probably would have written this in a way here. I would have said, if this head is equal to null, if I'm dealing with the empty list, then I'll just go ahead and call AddFront with that payload. Because if you're looking at an empty list, AddFront and addEnd, same function. Right? Why reinvent the wheel? If the list has nothing in it, the front and the end are the same place. So I just asked this quick little if statement. If the list is currently empty, if head is equal to null, just go ahead and call AddFront. Already wrote it. Otherwise, list isn't empty. So let's go ahead and create our new node. Now I need to run to the end of the current list. So I'll create a node pointer per node and start this guy off at head. A picture here. I called this guy per node. And I made him point to the same thing as head. Now I don't want to change the value of head. Because if I change the value of head, now I've lost the front of the list. So that's why I created a second variable here called curnode, so I can change him to start walking down the list until I get to the end. And I want to keep setting curnode equal to his own next node, as long as his next node is not equal to null. while cur node get next node is not equal to null, cur node is equal to cur node get next node. Set cur node equal to his own next node over and over and over again, as long as cur node's next node is not null. As soon as I get here, cur node now points to a place where his next node is null, which means cur node currently points to this dude right here in our example. And now I can say cur node set next node to n. Make sense? So addEnd 31. And there's our updated list, 3, 2, 1, with a 31 now added at the end. All right, make some sense? All right, so your homework write removeEnd in linked list. Make sure you manually delete memory. Let's just say, like we did in removeFront, so that the OS does not need to do it for us. So I'll go ahead and put in the placeholder stuff here for us. We're going to say void removeEnd. Actually, it's not void, it's going to be an int removeEnd. Grab my link again. All right, questions, comments, concerns, bribes. All right, so should be more practice with pointers, okay? All right, I'll see everybody on Wednesday. I did put a note up on Slack about the a couple different things. Student, faculty, staff Bible study starts tomorrow at noon, comes with free lunch, God and grub. Go down to the cafeteria at noon, sign in, get your free lunch, take it down to the terrace room. It's a pretty cool Bible study. I also put up stuff last week about CU Launch, the entrepreneurial event here on campus, where you just have to come up with an idea. Email Dan Sem, is the dean of the business school, and I try to get our students involved in that. You learn how to make a business model. You're basically committing to like 3 nights during the semester, and you get free food at every single one of them. And you have a chance of winning $2 grand. And we've had many students win the full prize. Usually not very many people do it. They sit here like you and like, oh, that sounds like a good idea. Never actually do it. And there ends up being 4 teams and they all get money. So do it is what I'm saying. All right. I'll see everybody on Wednesday.